Cancer is the second leading cause of death globally, and of all the forms of cancer, skin cancer is the most prevalent, with 5 million cases estimated to be diagnosed in 2020 in the USA alone. However, the estimated 5-year survival rate of skin cancers with early detection is as high as 99%, making early detection extremely important. The computer-aided diagnosis of skin lesions offers certain advantages, such as generating quick, robust, and reproducible results to assist diagnosis and serve as the source of a second opinion, along with reduced diagnostic costs and increased accessibility of dermatological expertise. Apart from often being the first step in the diagnosis, segmenting the skin lesion offers an added sense of trust in the predictions of automated algorithms. Moreover, some skin lesion diagnosis approaches rely on lesion segmentation to attend to the regions of interest in the image. Despite several improvements and advances in deep learning-based segmentation of skin lesions, most of the approaches tend to ignore illumination and color-based information from the images, an area which has been actively researched in the past. As we can see in this image, depending on the image acquisition setup of the lesion, lesions belonging to the same diagnosis class can appear vastly different. There is very little literature incorporating color-related information and multiple color space representations for deep learning-based skin lesion segmentation, and our goal with this paper is to leverage knowledge about the illumination and skin imaging in a deep learning-based skin lesion segmentation framework. We first begin by selecting certain color channels from the lesion images. The normalized RGB color space has been shown to compensate for uneven illumination as well as shadow and shading effects, and therefore we choose the red channel from the normalized RGB color space representation, denoted by R'. We also choose the complement of the value channel from the HSV color space representation, denoted by V*. They are calculated as here. The V channel can directly be estimated from the RGB color space without obtaining the HSV representation of the entire image. Here are 3 skin lesions along with their original RGB images and the corresponding R' and V* channels. The presence of shadows in skin lesion images can degrade the performance of segmentation algorithms, so our next step is to estimate an illumination invariant, also known as an intrinsic image of the skin lesion. Such an image depends only on the reflectance properties of the skin. Here is how intrinsic images are estimated using camera calibration. First, a color checker is imaged under multiple luminance. Here is a 2D log chromaticity plot for 7 patches from the color checker, such as green, blue, purple, yellow, etc., imaged under 10 luminance. Next, we estimate the invariant direction. However, this process is camera dependent, and ideally we would want to find the invariant direction without imaging the skin lesions more than once. Looking at this figure, we can see that the invariant direction is the one along which the projected image has the minimum entropy. So here's an overview of the approach. Given an RGB image, we calculate the 2D log chromaticities and the entropies for projection angles from 0 to 180 degrees. We then find the angle corresponding to the minimum entropy and use it to estimate the intrinsic image. Here are the intrinsic images for the same set of 3 skin lesions. For the first lesion image, we see that the inconsistent illumination in the bottom right of the image has been resolved in the intrinsic image. Next, we want to calculate a grayscale representation of the skin lesion image based on biological and optical properties of human skin and the physics of image formation. We consider the optical density space, where the skin image pixel RGB triplets have been shown to reside on a plane and are mostly distributed along a vector. Given the RGB image of a skin lesion, we plot the optical density space representation, and we notice that most of the values are spread along a single vector. When we carry out PCA on this, we observe that 98.3% of the total variance can be explained by the first principal component. Therefore, given a skin lesion RGB image, we project it along the first principal component to obtain a grayscale representation. Here are the results for the grayscale images, denoted by gray, for the same set of 3 skin lesions. Finally, we look at shading artifacts in skin lesion images. These are induced usually while imaging the non-flat regions, especially lesions, and can degrade the segmentation performance, and therefore our goal is to attenuate the shading effects. We do so by normalizing the illumination with respect to the intrinsic image, and we obtain the illumination by using the value channel from the HSV color space representation. Here is an overview of the approach. Given an RGB image of a skin lesion, we obtain its HSV representation. We also estimate the intrinsic image for the lesion and use histogram matching to match the value channel from the HSV image to the intrinsic image. We then replace the value channel in the HSV image with this new histogram matched value channel and convert the image back to the RGB color space, giving us the shading-attenuated RGB images. Here are the shading-attenuated images denoted by SA for the same 3 skin lesion images. Here's an overview of the method. Given an RGB image, we obtain the aforementioned color channels and illumination-based transformations, which we then concatenate channel-wise to the original RGB image. This, along with the segmentation masks, is used to train our lesion segmentation model. We used 3 datasets for our experiments: the ISB-ISIC 2017 Skin Lesion Segmentation Challenge dataset, the Dermofit Image Library, and the PS2 database. Since the Dermofit dataset does not come with training, validation, and testing partitions, we split the dataset in 60:10:30 ratio. Since the PS2 dataset contains only 200 images, we use the entire dataset for evaluating models trained on the Dermofit dataset. To compare and evaluate the contributions of each of these transformations, we conduct an ablation study. We train and evaluate 7 models on the ISIC 2017 datasets. The first model, called RGB only, takes only the RGB images as input and predicts the lesion segmentation masks. We then train a model by concatenating all the transformations to the RGB image, and we call this all channels. Finally, we train 5 more models by dropping 1 transformation at a time from all channels. The quantitative results show that all channels yields a considerable performance improvement over RGB only. Next, we observe that dropping the R- and V* channels lead to minimal segmentation performance drops, and this can be explained by the fact that these are fairly easy transformations for the network to learn. On the other hand, dropping the intrinsic channel leads to the largest degradation in segmentation performance, indicating that it might be difficult for the network to learn the specific transformation. Looking at the qualitative results, we observe a similar pattern where dropping the intrinsic channel leads to the degraded segmentation performance with more false positive and false negative predictions. Finally, we train 2 models on the Dermofit dataset. Apart from the RGB only model, we choose to train the no SA model because shading attenuated images are expensive to compute and do not add much to improving the segmentation performance. We evaluate these 2 models on the Dermofit dataset as well as on the entire PS2 dataset to test the generalizability of the models. The quantitative results show that using the color channels and illumination-based transformations lead to improvements in the lesion segmentation performance. To summarize, in this paper, we propose a deep learning-based skin lesion segmentation approach to incorporate information from certain color channels and illumination-based transformations. We evaluated the proposed approach on 3 datasets, and our results demonstrate the potential value of leveraging such information. However, it is unclear why a deep learning-based model trained on RGB images only is unable to learn these transformations, and therefore future work direction might be to learn to estimate these transformations in an end-to-end deep learning setting. Thank you.